to quantum gravity, but it is better than Newton's theory of gravity. So again, I've drawn them in hierarchy. This is the top dog. We don't have that theory yet. This is the next approximation. This is the first approximation, which we got in 1916. What we're going to talk about is this approximation, which Newton gave us in 1687. Okay. So this theory is good enough if you are near the Earth and you want to describe the gravitational field of the Earth and so on, small objects. Okay. So this theory is good when objects are moving slow compared to the speed of light and the gravitational field is weak. If you're moving very fast and you're near strong fields, then you need the general theory of relativity. Okay. Special theory of relativity is, needed when objects are traveling fast and there's no gravitational field. So, yeah. So general theory of relativity combines this and this for strong fields. And again, this theory is not good enough to describe, for instance, what happens inside a black hole. We don't know. Okay. Or if you want to describe the Big Bang and very phenomena right after the Big Bang, you would need this theory. So one of you guys can go discover that theory and win yourself a prize. Okay. So again, we're going to talk about this guy. Okay. What Mr. Newton said was every object attracts every other object in the universe. It doesn't matter what it's made of. Okay. So every object attracts every other object. And what Mr. Newton gave us was the magnitude. So this object attracts him, and the force is directed between the center of gravity of this guy. It's along the line connecting the two centers of gravity. And Mr. Newton gave us the formula for the magnitude of this force. Okay. The magnitude of this force is given by the gravitational constant times the product of the masses divided by the distance squared. Okay. So that's Newton's law of gravity. So let's see. If you double the masses, both the masses, then the force will increase by a factor of 4. If you reduce the distance by a factor of half, if you bring them half as close, then the force would increase by a factor of 4, and so on. Okay. This law was given to us by Newton in 1687. But we didn't know this constant. This constant was discovered in 1800, 100 years later. All right.
Yeah, so the universe is expanding, right?
Uh-huh.
Then if this law is true, how is that possible that the universe is expanding if objects are being attracted to each other?
So if I toss this, the Earth is pulling it down. Because I gave it energy, it was rising, but it was slowing down. Okay. So now instead of the keychain, we'll talk about these are galaxies. So what you said is correct. So all these guys should be, so this is going away. The gravitational force of attraction should be slowing these guys down, the expansion. So, and that's what scientists believe. And in fact, they were trying to measure the deceleration parameter. Okay, see, this thing is decelerating, and they named it the deceleration parameter because that's what they believed it to be. In 1998, to their shock, they found that it is accelerating instead of decelerating. They had this data for 2 years. They sat on it for 2 years, and they were afraid to publish it. How can you make it expand, accelerate? What accelerates? Hmm? Yeah, you just saw that rocket go up. If you have a source of energy, that can make you accelerate. So there comes the dark energy. Okay, so you're looking for dark energy. Okay, so currently the composition of the universe is so 70% dark energy, 5% normal matter, and 25% dark matter. Look at this. 95% of the universe, we don't even know what it is made of. Dark energy just means we are in the dark about the nature of that energy. Dark matter means we are in the dark about the nature of that matter. You and I are made of only, the stuff we are made of is only 5% of the universe. Okay? So, all right, so again, here's an interesting fact. Newton gave us this formula for the magnitude of the force back then, and this constant was not found till 1800, 100 years later, 110 years later. Okay? And the reason it wasn't found was because this is the smallest, this constant is very small, and it's called the universal gravitational constant. Why do you call it the universal gravitational constant? I'm sorry?
It's the same everywhere.
It's the same everywhere, and it's the same for all objects. So if you have two bears, the constant is the same. And if you have the Earth and the Moon, the constant is the same. So it doesn't care about the nature of the material. Okay? Yep.
How do you find that number?
And we'll talk about it. Okay. All right. So that was measured by Mr. Cavendish in 1800. So gravity is the weakest of the four forces, and that's because the gravitational constant is very small. So what are the four forces? What?
Strong, weak, electromagnetic, and gravity.
Strong, electromagnetic, weak, and gravity. And we've seen a table like this, table before. If the strong force is 1 unit strong, the electromagnetic force is 100 times weaker. This guy is 1,000,000 times weaker, and this guy is, you don't even bother talking about it. Okay, it's that weak, very weak. Okay. All right. So since this constant is very weak, if you want this force to be noticeable, then at least one of these masses has to be large. If both the masses are small, then this will be not very small force. Okay, so just to illustrate that, okay, so again, here's the force. Okay, if these two masses are small, then the force will be small. So for instance, you take these two masses are small, and the force between these two objects will be tiny. The force between these two objects is 10 to the minus 7 newtons, less than the weight of one of your hair. Now, on the other hand, the force between this object and this object is large, is noticeable. That's because the weight of mass of this guy is large. Okay, so if you put that to be the mass of the Earth, then the force between these two guys is strong. So the force between these two guys is 1,000 newtons, which is 10 billion times greater than the force between these two guys. Okay, so the force between these two guys is 10 billion times greater than the force between these two guys. That's why if you jump off the table, if I jump off the table, I won't fall toward her, but I'll fall toward her. Okay. All right, now the forces, uh, gravitational force is between all objects. So, galaxies attract each other and so on. Okay. And if they're headed towards each other, they'll collide. So, for instance, our galaxy, Milky Way, is supposed to collide with the Andromeda galaxy in 4 billion years. Okay. We're headed toward each other. Okay, so now the measurement of G. All right, so again, I'll sort of simplify this. Okay. Like I said, this constant was not measured till 100 years after Mr. Newton gave us the law of gravity. Okay. And this experiment is considered one of the more beautiful ones, and it's called weighing the Earth. Okay. So here's the idea. You take a metal wire and have two spheres attached to it. Okay, so here's the metal wire. Okay. So here's the metal wire, and you have these two spheres attached to it. Okay, what you can do is you can twist the wire and measure the force that takes to twist it. So what you can do is you can you could attach a spring to it and pull on the spring here. So you can find out what torque will twist this wire. So you can ask what torque will twist it 1 degree, and you can do that experiment. Okay, that's easy to do. And stiffer the wire, the greater the torque is needed to twist the wire. All right, so now you place this guy. So let's do this. So now you have made a measurement like this. So here's this thing. Here are these two little spheres, and you measured the stiffness of the wire. Okay, so you measured this. And now what you do is, so you have this thing, and then you bring up, so here are these two spheres, and then from far off you bring two large spheres. This large sphere will attract this guy. This large sphere will attract this guy. And what will it do? It will twist the wire. But you knew how much force was needed to twist the wire. So now you can calculate the force between these two guys. So what did you do? You bought large spheres, and that attracts this guy and that guy, and twists the wire. Okay, so the wire twists. The only problem is you bring these spheres up, so the force is G times m1 m2 divided by r square. Okay. Now the force is related to the angle through which it twists. You measure that angle. You measure this, and you know this force, and since you know this and this, you can calculate that. The problem is this angle, the twist is very small. It's less than 1/10 of a degree. So how do you measure that? What do you use to see an amoeba? A microscope. You need some way of magnifying small objects. And here is Mr. Cavendish's genius. So what he did was, he took a laser beam, put a mirror on the wire, and this laser beam shines off of there. So this wire, here's a laser beam, it's twisting, the mirror twists a little, and that beam moves a large distance. So that's a magnifier. There you go. So I knew that was coming. So you used a beam of light. They didn't have lasers back then. Yep.
Do you use like rotation formula or something like that?
And so no, well, you still have to measure how much, what angle. Yeah. Now, Valencia, I mean, that's a very sensitive instrument. Valencia State College has that instrument. Yeah. All right, so now here's okay. So this is called weighing the Earth because till 1800 we had no idea about the mass of the Earth. Okay, well, so we've known for about 2,000 years that the Earth was a sphere. We had measured the radius. Egyptians had done that 2,000 years ago. So the mass would be the density times the volume of the Earth. So we've known this. Now the density, you can go outside and get a handful of dirt and get the density. Okay? But how do you know that the density is the same inside? Okay, so you could calculate the lower limit, so to speak, for the mass of the Earth. But we really had no idea about the exact mass. All right, look at this formula. So this is the acceleration due to gravity on the surface, which we've measured, 9.8 meters per second. We've known this for 2,000 years. And soon as this was measured in 1800, now suddenly we have the mass of the Earth, the accurate mass of the Earth. So Mr. Cavendish measured that, and suddenly he knew the mass of the Earth. In fact, that's when we knew the mass of the sun and all that kind of stuff. Okay. So it turns out that if you go outside and measure the density of dirt, that's about 2.5 grams per centimeter cube. So once you know the mass, you could calculate the average density, and it turns out to be 5.54 grams per centimeter cube. So now you suddenly know that stuff gets denser as you go inside. All right, so here is the density profile, and we'll talk about this in a second. Okay, so this density profile, this we've known only for about 50 years, 40, 50 years. Okay, so here's the surface density. There's the center of the Earth. At the center of the Earth, the density is about 14 grams per centimeter cube. On the surface, it's about 2.5 grams per centimeter cube. Okay. So again, this graph is only about 50, 60 years old, 60 years old. Okay. So how do we know this? This picture is, like I said, only about 60 years old. Okay. Now, here's the deal. So you shoot a beam of light like this, and what happens is this beam of light will bend. Any wave, if it goes from one medium to another, it will bend if its speed changes. If the speed of the changes, and the speed will depend on the density of the material and other properties of the material. So any wave will change its direction if its speed changes. And this phenomenon is called refraction. And this happens for earthquake waves as well. So let's say here's an earthquake happen, and these waves are traveling. And you see this wave is bending. So why did it bend? I just told you. Because its speed is changing. And its speed is changing because the density of the matter is changing and all that, among other things. Okay? So the bending is related to the property of the material there. Okay? So here's an earthquake, and we have seismometers all around the Earth. So we can calculate. So here's the earthquake, and then it came at this time. Okay, so we know what time the earthquake happened and when this wave reached, when this wave reached, when this wave reached. Okay, so they collected earthquake data from millions of earthquakes, from hundreds of thousands of seismometer They put together all that information in computers and are back calculate the structure of the Earth. So this picture has been possible only since we've had large computing power. So this picture is still being refined. It's only about 40 years old. Yeah. Gravity outside an object. So here is a satellite going around. Okay. And okay, the gravitational force on it depends only on this distance. Now if you shrink this object to a point object, the force on it doesn't change. So for instance, here's this International Space Station. And let's say you go home and turn the Earth into a black hole. The orbit of the International Space Station would be exactly the same. Yep.
Is the density still the same?
What's that?
The density of the object is still the same?
No, the density will increase tremendously, but it doesn't matter. Its total mass is what matters. Okay. Okay. So once you're outside the object, the force of gravity on it is independent of, for symmetric distribution, the size of the object. So you can turn this into a point object and the force of gravity would be the same. Okay. The superposition principle states the following. So let's say you have a solar system. You want to calculate the force on this object due to all these guys. You calculate the force on this guy due to this guy. You treat each pair independently. Okay. The force that this guy exerts on him is independent of the presence of the other guy. Okay. So you calculate this force, then you calculate that force, and just add the two. And that's the net force on the guy. Okay. So this works for solar systems and all. But if you're playing with black holes, then it won't work. Yeah. But we won't be playing with black holes anytime soon. What is the acceleration due to gravity here? 9.8 meters per second squared. So the radius of the Earth, what is the radius of the Earth? 4,000 miles. Okay, so G is about 9.8 if you're close to the Earth's surface, or even if you're high. If the height you go is small compared to the radius, then you're fine. But let's say if you're 4,000 miles above the surface of the Earth, then G here is equal to G on the surface of the Earth divided by 4. So it's 2.5 meters per second squared. All right, so here's Newton's law of gravity. So if you're there, the force on you is mg. The force on you, g is the acceleration due to gravity at that point, is equal to g mass of the Earth times your mass divided by this distance squared. So g is that distance squared. And we are going to write this distance as the radius of the Earth plus the height. There's the radius of the Earth, and there's the height above the ground. Okay. And so now you can simplify this. You can pull the radius of the Earth out, h by r. And this gm divided by the radius of the Earth, that's 9.8 meters per second squared. So g at a height h is 9.8 meters per second squared times this smaller factor. So if you're at a height comparable to the radius of the Earth, then g decreases. So that's what they give you here. So the radius of the Earth is about 6,000 kilometers. See, at 6,000 kilometers above the surface of the Earth, g is 2.5 meters per second squared. Okay. Now, the International Space Station flies at about 400 kilometers. So in the International Space Station at that height, it's still about 8 meters per second squared. So that's illustrated here. See, G, the length of this arrow near the surface is 9.8 meters per second squared. But as you go further away, the magnitude of G is decreasing, and the acceleration is always pointing towards the center of the Earth. Okay? You see, these are all vectors, so this is a vector field. That's what we mean by. Okay? So the acceleration due to gravity is a vector field. Yep. The gravitational field is a vector field. Yep.
Is R the distance from the center of the object?
Yep. You're always measuring the R, the distance from the center of the object. Yep. If an object is going in a circular orbit, what is it that you need to make? Is it accelerating? What is the direction of the acceleration? Toward the center of the Earth. Okay. So you need centripetal. It is accelerating. It has a centripetal acceleration. What does Mr. Newton tell you if you have an acceleration? You need a force, okay, to make it go in that direction. All right. So let's say the Earth was not spinning, and you're standing on the Earth. The Earth is pulling you down, and this is your normal force. Okay, and since you're not moving, that normal force is balancing the force of gravity. Okay, now let's make the Earth spin. Now suddenly what happens? Okay, it's spinning, so now you need a centripetal force. Where is that centripetal force going to come from? Well, gravity is still acting. So now suddenly what you have to do is you have to make this normal force smaller. You make this small normal force smaller. You make this smaller force smaller. This minus this gives you the centripetal force. So the faster you spin the Earth, the smaller this force has to become. How fast does the Earth spin? Once every 24 hours.
Is that relative to the sun now?
I'm sorry?
No. I guess that
Mm-hmm. So can you spin the Earth fast enough where this goes to zero? If the Earth spun once in 90 minutes, this will go to zero. So the ground is not pushing you up anymore. You're feeling weightless. What's 90 minutes? Huh? That's the time it takes for the space shuttle to the International Space Station to go around the Earth. So if the Earth spun once in 90 minutes, you could walk off into space. You'd be weightless. All right, so, okay, so see, this is the North Pole. If you're spinning, if you're at the equator, you're going around. But if you're a Santa Claus, you're not going in a circle. So gravity is balanced by normal force, so there, oops. If you're on the North Pole, then this has to be balanced by the normal force. But if you're at the equator, if you're in New York City, you're going in a smaller circle. At the equator, you're going the fastest. You're going at 1,000 miles an hour. Okay. So mg, that's the gravitational force minus the normal force, provides you the centripetal force. Okay. And again, the faster you make the Earth spin, the smaller this has to be, because this is constant. Okay. And if this angular speed is 2 pi radians every 90 minutes, then this has to be 0. That's what we just said. Okay. So the effective gravity when you're going around, it turns out is g minus r omega squared. Okay, so you weigh about 0.35% less at the equator than at the poles. So at the equator, since you're going around, you weigh 0.35% less at the equator than at the poles. So a 100-pound person at the North Pole, if Santa Claus weighed 100 pounds, if he came to lived on the equator, he would weigh 99.65 pounds. Okay. Right. So you guys know how to calculate the speed at the equator. At the equator, while you're going around, again, the radius of the Earth is 4,000 miles. At the equator, the distance is 2 pi times that, which is 6 times 4,000, 24,000 miles, roughly. And you're taking 24 hours to go around, so 1,000 miles an hour. So if you're standing at the equator, you're going at 1,000 miles per hour. So here's another interesting fact. So here's the Earth, here's the North Pole. Here's the equator. At what speed are you going at this point? 0 miles per hour. Here you're going at 1,000 miles per hour. Here, if you're living in New York, you're going at smaller speed. I don't know, let's say 400 miles per hour. Okay, when you want to launch an object at low Earth orbits are 200 miles or something like that. So the International Space Station, for instance, is going at around 18,000 miles per hour, something like that. Okay. So if Santa Claus launched that International Space Station, he would have to go from 0 miles per hour to 18,000 miles per hour. You launch it from New York City, you'd have to go from 400 miles per hour to 18,000 miles per hour. So what is the optimal launching spot? Near the equator. Okay, so you want to be as close to the equator as possible. Yes, so you use as little fuel as possible. So we launched from Florida, that's close by. European Space Agency's launch from a floating platform in the sea near the equator. And of course, you have to go in the same direction as the Earth is rotating. All right, so here's another very interesting point. So here, imagine this is a building. Is the building perpendicular to the ground? I'm sorry? Yes. Okay. The building is not perpendicular to the ground. So this is not perpendicular to the ground. So in this room, that is east, that's the north side. It's tilted towards the North Pole. All right, so let's see this. Okay. So in the northern hemisphere, you're tilted towards the North Pole. In the southern hemisphere, you're tilted towards the South Pole. The only place where the buildings are perpendicular to the ground are on the North Pole, South Pole, and the equator. Okay, so let's figure this out. Did you guys understand that? Okay, so let's say you're building a building here. The Earth is spinning. Okay, so you're going in a circle like that. Okay, the building is going in a circle like that. To go in a circle, what is it that you need? You need a centripetal force toward that center. There is the centripetal force you need. So, okay, so here's a plumb bob. So this plumb bob this sphere is going in a circle like that, you need a centripetal force on it. Where is that centripetal force coming from? Well, there's the force of gravity. Okay. So there's the force of gravity on it. Well, I'll draw it like that. Here's the force of gravity on it. And the tension with which the plumb bob pulls has to be in that direction such that you get this centripetal force. These two, the force of gravity and the tension, add up to give you the centripetal force. So if this guy was in that direction, you wouldn't get that centripetal force. So you see this thing is tilted, the bob is tilted towards the North Pole. And that's, you're using the plumb bob to build a building. And so you're building the building like that. So any building built north of the equator is tilted like that. Okay. So for non-zero latitudes, Fs no longer points away from the center of the Earth. It's tilted towards the pole. A plumb bob will always point along this deviated direction. All buildings are built aligned along this deviated direction. For the tallest building, this represents a deviation of a few feet at the top. So for tall buildings, that distance is a few feet. So for tall buildings in the northern hemisphere, they're built like that. So every tower is a leaning tower of Pisa. So in the northern hemisphere, you tilt it to the North Pole. Yeah. So here's another very interesting thing. Okay, this is something Mr. Newton proved. Okay. So let's say if this was a basketball, and if we were inside a basketball, what Mr. Newton showed was, what is this piece of the basketball going to do? Attract you in this direction. What is this piece of the basketball going to do? Attract you in the opposite direction. And it turns out that this piece, the force due to this piece and this piece, exactly cancel. So the force on you due to these two pieces is zero, no matter where you are. So if you're here, this piece will cancel the force of this guy. So if you were inside a basketball, no matter where you are, the net force on you is zero. All right, that's for a symmetric distribution. Okay, so if this is the Earth, if you're here, it turns out that the only force attracting on you is this guy. All this guy has zero force on you. So if you were at the center of the Earth, what is the force on you? I'm sorry? Zero. Okay, so if you analyze that, what happens is the force on you at the center is zero. If you're here, the force on you is due to the entire Earth. If you're here, the force on you is due to this part of the Earth. So as you go deeper and deeper into the Earth, the force is getting smaller and smaller in you. So the force on you at a distance r from the center is that given by that. Okay, this is a constant. That's g is a constant. Rho is the density of Earth. M is your mass, and so on. Okay, this force is exactly like this force. What is this force? The spring force. That's the spring constant. So this acts like a spring constant, and this is like that. So what does a spring do to you? The motion of the mass attached to a spring. So you attach a mass to a spring and it oscillates like that, like so. All right. So let's say you dig a tunnel through the earth like that. By the way, what is the radius of the earth? 4,000. The deepest hole we've dug is 4 miles, so we barely scratched the surface. So we'll never be able to dig this tunnel. But let's say you dig this tunnel, and you step into this tunnel. You'll oscillate exactly like that mass attached to the spring. When you go to, when is the mass attached to the spring going the fastest? I'm sorry? When is it going the fastest? So right in the middle is when it's going the fastest, okay? So just like that, you'll be going the fastest at this point, okay? So you step on this tunnel, you'll be going the fastest. And the speed you'll be going at is 18,000 miles an hour. Do you remember that speed? I'm sorry? And that's the speed of the space station. Okay. How long does the space station take to go around? 90 minutes. You'll take 90 minutes to complete one oscillation. So those two motions are related. Yep.
Would you be going forever?
Yeah, you'd go forever if there's no friction. Yep. So you can step into this tunnel in New York, go to Tokyo for lunch, get sushi, and come back.
You're not
What's that?
obliterated by then.
What's that?
You're not obliterated by then.
All right. So you'll learn in a later chapter that uniform circular motion is two simple harmonic motions. It's a combination of this simple harmonic motion and this simple harmonic motion. Okay. Here's okay. So if the Earth had constant density, then the acceleration due to gravity would be the greatest on the surface of the Earth and decrease to zero as you're going to the center of the Earth. Now, it turns out that the density is not uniform, and so it turns out that since the Earth is much denser here, the acceleration due to gravity is highest about at a radius of about 3,500 kilometers, and it is about 10.5 meters per second at that depth. Okay. All right, so in this tunnel, the period of oscillation is 85 minutes, okay, the same as that for an International Space Station. We saw the expression, I'm not going to derive this, we saw the expression for the gravitational potential energy. What was you guys remember what is the expression for gravitational potential energy? mgy. Okay, this expression is good as long as g is constant. When is g constant? If you're close enough to the surface of the Earth. Okay, so if you don't jump too high, let's say you don't jump 300, 400 miles, then you can use this expression. But if you want to go far away, then you can't use this expression anymore. So the correct potential energy, the correct expression for potential energy is minus g mass divided by r. And r is the distance between the center of gravity of these two masses. Okay? So this is the correct expression for U, for the potential energy, except that this is a pain in the neck to use. Okay? So for instance, these 4 people that went on a ride yesterday, those guys have to use this. They're going 250,000 miles away. Okay? So they would have to use this. So there's the correct expression for U, gravitational potential energy. U, R is this distance. That is all. Okay. So if you have a constellation of particles, so if you have a solar system, for instance, and you want to calculate the gravitational potential energy of this solar system, you calculate the gravitational potential energy of this pair plus this pair plus this pair. And that's what this is. Okay. So that's the gravitational potential energy of that system. So if that system was at rest and you want to break it apart, send all these particles to infinity, that's how much energy you would have to add to this system. Okay. So for instance, here's a case. So let's say Sophia is sitting on her chair here, and the gravitational potential energy of Sophia and the gravitational potential energy of that system is that. Now let's say we want to get rid of Sophia, send her to space, to infinity. You would have to add this much energy. How can you add that much energy? Shoot her from a cannon. Yeah. How much so what would that correspond to? This energy would correspond to, if you shoot her from a cannon at 11 kilometers a second, she'd go to space. She'd escape Earth's gravity. That is called escape velocity. Okay? So for instance, see, I tossed this guy. I didn't give it enough energy and it came back. I shoot it with a higher speed. It went higher, but it still didn't have enough energy. Okay? So if I throw this object at 11 kilometers a second, so from the surface of the Earth, the escape velocity is that. Yep. Mm-hmm.
Will it go faster if it's...
So if you shoot the object at escape velocity, it'll escape no matter what direction you throw it at. Yeah. So every object, there's a escape velocity from every object. From higher up, see you would replace this r by r from the radius. So if you're shooting from higher up, then the escape velocity will be smaller. Okay. Yep.
You said the escape velocity for the Earth is
11.2 kilometers a second. Okay, so here's something very interesting. What is the fastest anything can travel? Speed of light. Nothing can travel faster than the speed of light. Okay, so let's just for giggles make the Earth squeeze the Earth. So what are we doing? We're decreasing this. What's happening to the escape velocity? It's increasing. So you're decreasing this and the escape velocity is increasing. Or you can increase the mass and the escape velocity increases. For a given object, you decrease the radius, its escape velocity is increased. So you decrease the radius such that the escape velocity becomes c, the speed of light. It's become a black hole. That's what a black hole is. Okay? So if you squeezed Earth to the size of a marble, about that big, it'll become a marble. It'll become a black hole. But the thing is, if you squeeze something to that size, it's, as far from everything we know, it doesn't stop, it just keeps falling. We don't know what the final thing is. But if you squeeze it inside of there, the escape velocities become a black hole and, no information from inside can come to you. So The sun is, if you squeeze the sun to within 3 kilometer radius, 3 kilometers is from here to Bethune-Cookman College, the sun would become a black hole. Yep. All right, so here's the escape velocity from various objects. So escape velocity from various objects. From the Earth, it's 11.2 kilometers a second. From the surface of the sun, it's 600 kilometers a second, and so on. From the moon, it's 2 kilometers a second. Yep.
The escape velocity
Mhm.
11.2, is that for the entirety of the Earth or would it be faster at the center?
Say that again.
Like, so if we were on the surface of the Earth, it's
Mhm.
11.2. If
Mhm.
we're at the center of the Earth, would it be faster?
Uh,
Or is it still 11.2?
so it would be slightly faster. Okay. Here's how. So if you're at the center of the Earth, there's zero force on you. But as you're coming out, there's a force on you. So you got to spend energy to get to the surface. And then you have to go at 11 kilometers. So it will be slightly faster, but not that much faster. No, it could be faster. I don't know the exact number. It'll be faster. All I can say is it will be faster. All right, this kind of stuff is important. Okay. By the way, the Artemis mission that we've sent, so Earth, Moon. So they're going to go like that, and then this time. So we'll be going this is the furthest that the human has ever been from Earth. And the reason we are going that far is because we don't want to get. We're going 5,000 miles from the surface of the moon, because we don't want to get caught up in the orbit of the moon, in the gravitational force of the moon. So here, the force of the Earth is greater than the force of the moon. Why is that?
Closer to the sun.
I'm sorry?
Closer to the sun.
Because we don't want to get caught up in the gravity of the moon. If you go close to the moon, then you need more rocket fuel to get out. So you're just going to go that far and then just fall back to Earth. So, all right. Now, the moon doesn't have any atmosphere. The reason it doesn't have any atmosphere is if you put any gas in there, see, the escape velocity is so small and the temperature will be high enough where all the molecules will escape. And that is why we don't have hydrogen in our atmosphere and helium in our atmosphere, because those molecules are light enough, and at these temperatures they'll move fast enough where they'll escape the Earth's gravity. Okay, so if you go to Publix and buy a helium balloon and let off the helium, all that helium will eventually escape. Okay, so to predict the atmosphere of a planet, you need to know the escape velocity and the temperature. The hotter the temperature, the less atmosphere it'll have. Okay? So if the average velocity of a gas molecule is 1/6 the escape speed, then the gas will not be present on the planet. Yeah. So the atmospheric composition of a planet is determined by its escape speed and average atmospheric temperature. Okay, so Mr. Newton gave us the formula for the force, and the force was, okay, G is the gravitational constant, that's the masses of the two objects, and R is the distance between them. Okay, so if the force between two objects is an inverse square law, then the only possible orbits are conic sections. So here's a cone, and you can take sections of the cone So they're conic sections. Okay. So all motion caused by inverse square law is one of the 4 conic sections. Okay. So if this was massive, the orbit of this guy around this guy is only and this is saying this is a large object and this is a small object. The orbit of this guy can be a circle or an ellipse, and it's a circle or an ellipse if it's a bound orbit, meaning the total energy is less than 0. Or it can be a parabola. A parabola corresponds to total energy equal to 0. Or a hyperbola, this is energy greater than 0. But the orbit of this guy can only be one of these 4 possibilities. So the total energy of a planet going around the sun, the total energy is less. Total energy is potential energy plus kinetic energy. The potential energy of a planet is that plus 1/2 mv squared. Okay, and the total energy of the Earth and any planet that's bound to the sun is less than 0. So it can either be a circle or an ellipse, and since this is a random thing, the orbits of all planets are elliptical around the sun. So that's what Mr. Kepler says. Okay, planetary orbits are ellipses around the sun, with the sun being at one of the foci. Okay, so here's an ellipse, and here are the focal points. So planets go around the sun. Okay, and the other focal point is empty. So this is empty. Kepler's second law states that, and these were the observations he made. So here's a planet going around, and what he says was, the second law says, so let's say the planet goes around like that in 1 week. This is the area it swept out in 1 week. And later in a week, in 1 week period, it sweeps out equal areas in equal time intervals. So when it's further away, it's going slower, and when it's closer, it'll go faster, because the area it sweeps out equal areas in equal time intervals. Okay? And this is a consequence of conservation of angular momentum, but he didn't know that. Okay. And the third law says square of the orbital period. So what is the orbital period for Earth? 1 year, 365 days. The square of the orbital period is proportional to the cube of the semi-major axis. Okay. So if it was a semi-major axis is that, but if you take a circular orbit, it's proportional to cube of the. Okay. And that proportionality constant is the same for all planets. Okay. Okay. So those are Kepler's 3 laws. So Kepler's first law is a consequence of the inverse force law. Okay. So here's how planetary orbits look like. Here's the orbit of Pluto. Okay. And here is the orbit of Halley's comet. A comet's orbit is very eccentric. Here's the sun. For planetary orbits, their Earth's orbit almost looks circular. Okay? And how flat the ellipse is measured by something called the eccentricity. Okay? If the orbit is circular, the eccentricity is 0. Here is Mercury's orbit. What do you see? So we saw that if the force is inverse square law, then the orbit is one of these orbit is an ellipse. It's a closed orbit. So for Mercury, you see the orbit is not closed. The orbit is precessing. Now this is a very small effect, but that tells you that this force is not quite that, okay? So there is a correction to this inverse square law. And that was when Mr. Einstein came up with a better theory of gravity, an improvement on this law, that is the first thing he calculated. Okay. So the precession of Mercury's orbit is what he first calculated. Okay. See, the eccentricity measures how flat the orbit is. The eccentricity for Pluto is 0.25. Eccentricity 0 implies a circle. Okay. The eccentricity of Earth is 0.0167, so it's almost circular. Halley's Comet has an eccentricity of 0.97. Kepler's second law says that a planet sweeps out equal areas in equal time intervals, and it's a consequence. So this is the area swept out in this time, so this is constant, and it's a consequence of the angular momentum of the planet is constant. Yeah. See, it's amazing. This is an electron going around a nucleus, and it goes in orbits where the angular momentum is constant, just like a planet. Okay. So here is laws of physics governing the microscopic and the macroscopic. The same law. So the Kepler second law says, so it's a planet is sweeping out equal areas in equal time intervals, and that's because the angular momentum of that planet is constant. Kepler's third law says, okay, so the period square of the planet divided by the radius cube is related to the central mass. That's the mass of the sun. So what is the orbital period of the Earth? 1 year. What is the Earth-Sun distance? I'm sorry? Yeah, 92 million miles. So you know this and you know that. Go home and calculate the mass of the sun. See, Mr. Cavendish measured this in 1800. So in 1800, that afternoon, we knew the mass of the Earth. That afternoon, we knew the mass of the sun. See, that was a very important experiment. Till then, we had no idea about the mass of the sun. Okay, so go home and calculate the mass of the sun. It's an interesting. Okay, so look up the radius accurately and all that, and see how close you come to the mass of the sun, which is 2 times 10 to the power 30 kgs. Okay. So here is T squared by R cubed for various planets. Okay, imagine this. Mr. Kepler didn't know this. All he had was data of planets going around the sun, and he didn't have a calculator, remember? And he calculated for all these planets, he calculated this ratio. T squared the period divided by the radius cubed. And you see for all planets, it's the same number. So that's how we got the mass of the sun. Okay. So in fact, if you know the period of any object circling a central mass, okay, so for instance, so you can use this formula this can be the International Space Station, and the International Space Station essentially is skimming the surface of the Earth. You know the radius of the Earth's International Space Station, that's 90 minutes. You know the radius of the Earth, which is 6,400 kilometers, and you can get the mass of the Earth. Okay. So if you know the period of any object that's going around a massive object, and you know the orbital radius, you can calculate the mass of the central object. Yep.
So like, if you wanted to calculate the mass of a black hole, you use the stars around?
So all galaxies, at the center of all galaxies, there are massive black holes. That's exactly what's being done here. Okay? So these are stars that are going around a central object that we can't see. Okay? And this lady, she might have won a Nobel Prize for it. I'm not sure. She did exactly that. Okay? In the 90s. Nobody was doing that, but she did that. So you looked at stars going around a central massive object, and here are these stars going at crazy speeds, 40-50% the speed of light. Okay. So that's how you find the mass of any central object. All you have to do is look at some object orbiting it. The more massive this object is, the faster it has to orbit at a given radius. So you measure the period square, the radius cube, and that's proportional, inversely proportional to the central mass. Yep. See, that's why I keep telling you, you're learning everything. The basics are here. You learn stuff here, and that will lead to all kinds of. All right, so there's Kepler's third law. So to find the central mass, all you need to do is measure the radius, period, and the radius. Okay. So if you want to orbit at a distance r, that is the speed you need to have. So you can calculate the orbital speed of anything. So the orbital speed of the International Space Station is 8 kilometers a second. What is the escape velocity from the Earth? I'm sorry? 11 kilometers per second. See, this speed is less than that. That's why it's bound. If it wanted to escape, then it would have to speed up to 11 kilometers. All right, we'll stop here.